Okay, our final topic this week is going to be coordinate vectors. So typically if we're talking about a 3D space, we like to talk about vectors that look like, say, some xyz. And here when we say that we have xyz, we're saying that we have x coordinates in the, or x movement in the x direction, y movement in the y direction, and z movement in the z direction. So we get this vector kind of as a result. The truth is, when we're saying these things, what we're really looking at is talking about things with respect to the standard basis for R3. And this makes sense because we're usually used to thinking about kind of the standard basis of coordinates to start off with. Recall that the standard basis for R3 is 1, 0, 0, 0, 1, 0, 0, 0, 1. So using that standard basis, if we have some vector x, y, z, it's very clear to us that we just have this is equal to x times 1, 0, 0 plus y times 0, 1, 0 plus z times 0, 0, 1. So here, the coordinates are just the scalars in the linear combination. That's what we're really meaning by the coordinates. Notice that if we had the coordinates for the vector 1, 2, 3, the coefficients would be 1, 2, and 3 respectively. So 1, 2, 3 is the same as 1 times 1, 0, 0 plus 2 times 0, 1, 0 plus 3 times 0, 0, 1. But one of the things we found out when we were talking about bases is that bases are not unique, right? This is not the only basis we could have, and so let's consider a different basis. Let's consider the basis 1, 1, 1, 0, 1, and 0, 0, 1. So let's try to figure out what the coordinates for our vector 1, 2, 3 would be in this new basis. What we would do is we would find the scalars alpha 1, alpha 2, and alpha 3 so that 1, 2, 3 equaled alpha 1 times 1, 1, 1 plus alpha 2 times 1, 0, 1 plus alpha 3 times 0, 0, 1. So going through the motions, which would be for us to get a matrix set up, so 1, 1, 0, 1. This is a 1. I don't know if me scribbling more makes that more apparent or less apparent. 1, 0, 0, 2, and 1, 1, 1, 3. And obtaining the reduced row echelon form of this system, we would get 1, 0, 0, 2, 0, 1, 0, negative 1, and 0, 0, 1, 2. And so here, by going through these motions, we're going to find that alpha 1 equals 2, alpha 2 equals negative 1, and alpha 3 equals 2. So thus we can represent it as a vector in coordinates according to this basis as saying that the vector 1, 2, 3 in terms of this basis is 2, negative 1, 2. So again, this is the same as saying that 1, 2, 3 equals 2 times 1, 1, 1 plus negative 1 times 1, 0, 1 plus 2 times 0, 0, 1. So we call this vector 2, negative 1, 2 the beta coordinate vector, or for our basis, or the coordinate vector relative to the basis b, and this is how we denote it, is v sub b. Notice that we're saying we're talking about our terms in terms of that particular basis, and so if we have multiple bases, we can talk about the same vector. So say that we had some vector w, and it was equal to alpha v1 plus alpha 1 v1 plus alpha 2 v2 all the way through alpha n vn, where these v's are in this first basis. Then the coordinate vector for w with respect to b1 will just be alpha 1 through alpha n. But say instead let me make this maybe a little more, or a little less B intensive. If we said that W was equal to some C1U1 plus C2U2 plus all the way through CNUN, then our coordinate vector for W with respect to our second basis would be C1, C2 through Cn. So we're really just storing the coefficients of the linear combination needed in order to obtain whatever vector this is. So here we're saying that if V is this 1, 2, 3, V with respect to the basis B we had up here would just be 2, -1, 2. But with respect to the standard basis, it's just 1, 2, 3. So notice that all of these coordinate vectors are going to look like vectors in Rn for some n. So let's do an example maybe that isn't in vector form. So suppose that we've got V, which is equal to 3 plus x minus x squared, and this is something in P2. We're going to give ourselves a standard basis for P2, 1x squared. So we can think of V, which is 3 plus x minus x squared, as 3 times 1 plus 1 times x minus 1 times x squared. So we define 3, -1, and 3, 1, and -1 as the beta coordinates, or the coordinates with this basis for V. So now we can say that 3 plus x minus x squared with respect to the basis B, this is just saying that we have our vector in terms of the basis for B. It'll be 3, 1, -1, because again it's 3 times 1, so 3 times 1 plus 1 times x minus 1 times x squared. So here we want to talk about whether or what the coordinate vector will be for 3 plus x minus x squared relative to the standard basis for P3, and then we want to know if order should matter here. So take a minute and see if you can tell me what the basis is, or sorry, what the coordinate vector is with respect to the basis S, and then we can talk about if the order matters. All right, you tried it? Great. So then if we wanted to write 3 plus x minus x squared with respect to S, take our vector and write it with respect to S, this will be 3, 1, -1, 0. So 3 times 1 plus 1 times x minus 1. matters. So we can kind of think of the coordinate vector for V relative to a basis as the instruction manual for how to put together those basis elements to create V. All right, so let's have vector space be equal to ax squared plus bx plus c, where a plus b minus 2c equals 0. So now we're going to have a specific subspace, and a basis for this is going to be -x squared plus x and 2x squared plus 1. So we've got a basis for this strange subspace. And what we want to do is we want to be able to describe some vector, 3x squared minus 3x, in terms of these vectors. So let's say we want to find the coordinate vector with respect to this basis. What we're doing is we're saying that 3x squared minus 3x equals alpha 1 times the first basis vector of x, negative x squared plus x, plus alpha 2 times our second basis vector, which is 2x squared plus 1. So if we kind of expand this, we're saying 3x squared minus 3x equals negative alpha 1 x squared plus alpha 1 x plus 2 alpha 2 x squared plus alpha 2. All right, so again, when we're setting up linear combinations for these polynomials, we're looking at the coefficients. So the 3 should match up with the negative 1, or the negative alpha 1, the 2 alpha 2. The negative 3 in front of the x should match up with the alpha 1 here. And then we don't have a term over here that's just a constant, so we'll assume it's 0. And we have to set that equal to our alpha 2. So then, looking at our system of equations, we get negative alpha 1 plus 2 alpha 2 equals 3. Alpha 1 equals negative 3. And alpha 2 equals 0. I want to pause for a second here. If you're having trouble at this point in the semester setting up these systems of equations, reach out. I know there are definitely people that, still could be maybe a little on shaky ground at this point, but this is very important for us to be able to kind of do anything with this class. So we could go ahead and put this system of equations into a matrix. What we'll end up seeing is that alpha 1 equals negative 3 and alpha 2 equals 0. So that means if we want to take 3x squared minus 3x and write it with respect to this basis, in other words, take our vector and write it with respect to the basis b, we'll end up getting negative 3, 0 as our coordinate vector. All right, so, that's weird. Something popped up. Still recording. Okay, great. So, we have our vector now, and that's great. So this is our answer, the first part. Now we also can say that we know the coordinate vector for some vector, and have it with respect to a certain basis, and want to figure out what the original vector was. So if we say that this vector with respect to the basis b equals 2, negative 1, what that tells us then is that w equals 2 times our first basis element, which is negative x squared plus x, plus negative 1 times our second basis element, which is 2x squared plus 1. So then if we go ahead and distribute through, what we get is negative 2x squared plus 2x minus 2x squared minus 1. And when we combine our like terms, we get that w equals negative 4x squared plus 2x minus 1. So we can take our coordinate vectors with respect to particular bases and use that then to kind of rebuild these vectors. All right, so let's go ahead and have you guys try to look at this next example and see if you can work through it. All right, so assuming you've given it a shot at least, let's say that we now had a different vector space, subspace, and we have two different bases for it. We've got b1 and b2. If we have a vector w written with respect to B, the first basis, as 1, 2, that tells us then that W equals 1 times 1, negative 1, 1, 1, plus 2 times 0, 1, 1, 2. So then combining our like terms, here we've got 1 plus 0, which is 1, negative 1 plus 2, which is 1, 1 plus 2, which is 3, and 1 plus 4, which is 5. So 1, 1, 3, 5 is going to be equal to W. We now want to be able to find coordinates for this vector in terms of the second basis. So Eva's basis is B2. So what we'll do is we'll take 1, 1, 3, 5 and try to write it as alpha 1 times 1, 0, 2, 3 plus alpha 2 times 1, negative 2, 0, negative 1. So using that second basis. So again, we need to set up a system of equations, and we'll kind of use each of these different parts of the matrix in order to set this equation up. So the first, using the top left entries, we should get alpha 1 plus alpha 2 equals 1. Using the top right entries, we should get negative 2 alpha 2 equals 1. Using our bottom left entries, we should get 2 alpha 1 equals 3. And using our bottom right entries, we should get 3 alpha 1 minus alpha 2 equals 5. And so we can use this to set up a system of equations, or use the system of equations to set up a matrix. So we have 1, 1, 1, 0, negative 2, 1, 2, 0, 3, and 3, negative 1, 5. And when we get the reduced row echelon form of this, we end up with 1, 0, 3 halves, 0, 1, negative 1 half, 0, 0, 0, 0, 0, 0. Now, if you look at this matrix and you firmly believe that this means it has infinite solutions, post something on the discussion board. We should have a chat, because rows of zeros do not make infinite solutions. We should maybe kind of clear the air on that as to why that is. What we see is that alpha 1 equals 3 halves, and alpha 2 equals negative 1 half. And so that means that if we wanted to take W and write it with respect to our second basis, we would end up with the vector 3 halves, negative 1 half. All right, now the next 2 pages here, or the next page rather, has an example that I want you guys to read through on your own and see if you understand. So part of the reason I want to give this to you guys as a reading example is I want to be able to kind of verify that you can start from the top of this, read to the bottom of this, and say, yeah, I understand kind of the logic and everything that's happening there. There's a lot of people who can't go from here to here without being tripped up at least twice. And so if you're one of those people who's having trouble kind of reading from here to here and understanding everything that's happening, again, I encourage you to post on the discussion board and ask any questions you may have.